Good evening. I hope I am audible. So I'll share my slides and we'll start the session. So this is Manchi Tripathi and welcome to Environmental Chemistry, week 8 of the problem solving session. So first what I will do is first we will solve few questions, then if the time permits we will study solubility equilibria in detail. Okay, so I'll share my slides. I hope it's visible. So, okay, so we'll start. So before going into this, what definitely we need to study about solubility equilibria is we need to study the solubility equilibria of slightly soluble salts, or the salts which are not completely like NaCl but slightly soluble in water. And all these things will be doing for the aqueous solution. That is very important assumption to consider. Secondly, effect of other solutes on salt solubility. If we have a particular type of salt that we want to dissolve and there is another salt that is there, so what will be the effect of both of them among each other? Thirdly, we'll study the removal of heavy metals from complex water and wastewater system. So these three are very important points that we'll be studying in this chapter. Okay, so the concept is even if we take NaCl, sodium chloride, that is common table salt, if we are dissolving in water, the water will be very, very clear. If we add some more, then again the water will be very clear. But if we keep on adding it, we will see that there is a point after which we will see the salt which is not at all soluble. We will see some solid portion. So that is the importance of solubility. It was soluble, but after a certain range, it is not. But if we heat the water, we can dissolve more and more salt. So this is important things that we need to consider here. So the when ions of that was completely soluble NaCl, it is forming ionic bond. But when the ion of a sparingly soluble salt are brought together in solution, it is observed that if the concentration of these ions is sufficiently large, so when the concentration is sufficiently large, a solid is formed that settles below the solution. So it settles in the bottom. So same happens for NaCl or even if we take sugar and anything. Okay. So if we, for example, if we see a solution like CaCO3. So if we are trying to dissolve this in water, what will happen? It will form Ca and CO3. It's going to form these. So if the concentration is relatively low, it is fine, we will not see. But if the concentration is very high, what will happen? We will see white color precipitate the side of our utensil. So actually this calcium chloride will give hardness also. So that is what the hardness that we see because it is no more soluble. So the formation of calcium carbonate may be observed to be it is time dependent. Like initially we will not see, but after some time we can observe this. So immediately there won't be any formation of calcium carbonate. This reaction will go in both direction. Okay. So immediately there is no formation of calcium carbonate, but after some time, after the short period time, the presence of very small particle of calcium carbonate can be noted, and we can observe this in the sides of the reactor or the container in which we are taking. So similarly, how we can observe this when we are boiling water, we will see white precipitate. Okay, if the water is completely boiled and it is evaporated, we will see some white precipitate over the sides. So why this is happening? This is happening because of the presence of calcium carbonate, or it can be presence of any other hardness. Okay, so um, okay, so we'll see first questions, then we'll see the concept. So consider the statement below and choose the statement that is true. There are 5 different options. Complexation generally increases the total concentration of metal ions in the solution. Okay, so what is complexation? It will take the metal ion and form complex. So it generally increases the total concentration of metal ions, or the extent to which calcium ion can be removed by lime softening to form calcium carbonate may be limited in part by soluble complexes of Ca2+. Complexation decreases the toxicity of metal ion, which predominate toxic species is the free metal ion. In the COD test, mercury salt is added, otherwise COD obtained will be underestimated. And during the hardness testing, we add EDTA, which allow magnesium metal ions to be free so as to give true endpoint of titration. What can be correct answer among these? So it all depends upon the complex formation and the solubility. Please solve this question. We'll see the solution. So these three are correct. The complexation generally increases the total concentration of metals in solution. The extent to which calcium can be removed by lime softening to form calcium carbonate may be limited in part by soluble complexes of Ca2+. Complexation decreases the metal ions, whose predominant toxic species is free metal ion. Okay, so here comes the concept of okay. Apart from this question, we should move forward with what is solubility. So, for the precipitation to occur, the solubility should be low. Okay, so that is important. If the solubility is very high, there won't be any precipitation. So there are different 3 types of solution: saturated, unsaturated, and supersaturated. Okay, so we know what is saturated and unsaturated solution. The example that I was giving for the, like, if we take a beaker in which there is some water and we started adding salt like NaCl. So if, like, say the water is 100 ml, so this is just example, not exactly, okay, 100 ml, and we add just 1 gram of salt. The water will be unsaturated because we can add more salt, okay. And if we add some 10 gram, still water is undersaturated because we can add more. But what if we add like 100 grams, 100 grams in 100 ml? So this is just an example. Maybe we can see small precipitates of NaCl. So in that condition, the water will be saturated. Okay. But the example I was giving, if we heat the water, okay, if we start heating the water, if we start heating it, what will happen? The solubility will increase. More salt can be dissolved. So at that time, this is called supersaturated solution. Okay, and the point is, like, if we are heating it, more NaCl can be dissolved. Maybe 120 gram NaCl can be dissolved. So that time it is called supersaturated solution. But if we put off the flame and keep it for maybe 1 minute or 2 minutes, 1 to 2 minutes, what will happen? Again, we will see particles of NaCl. So only a freshly, please note it down, only a freshly prepared solution can be supersaturated solution. Because as we leave a supersaturated solution, it gets time to form nucleation and it will start precipitating. Okay, so only freshly prepared solution can be supersaturated. Now there is concept called solubility product constant. So before moving into further question, it's better to see a few concepts here. So solubility product constant, which is determined by KSP. So it is the maximum concentration in which something can be dissolved. So for example, if solution is there AB, I don't have my writing device with me for now, so pardon me for that. AB, and it is forming AA plus PB. So KSP will be, and here also we can do things in terms of activity and concentration. Activity curly bracket and concentration square bracket. So activity will always be a correct term, but here we are taking it as ideal solution. So we will do in terms of concentration. So that will make our task easier. So KSP will be okay, A, capital A raised to power small a and capital B raised to power small b. So this is KSP, solubility product or solubility product constant. Okay. So here without precipitation up to KSP level, the things whatever A and B are there, ions, it can be dissolved. Okay. And the important point is KSP for a particular salt will be constant at a standard temperature and pressure. As I was saying, for this example, let's say KSP was 100 grams per 100 ml, but at a particular temperature, okay, and at particular pressure. If we change the pressure and temperature, the KSP will change. Okay, we change the temperature, right? What happened? Now 120 grams can be dissolved. So like that, pressure and temperature KSP can be changed. Okay, so what are the factors that affect the solubility? Okay. So factors that affect solubility are indifferent ion effect, common ion effect, effect of other salt, and complex agent. So this question number 1 is based on complex agent. So we add complex agent to increase the solubility. So it will be better to take one more slide and solve this. Okay. So one is indifferent ion effect, common ion effect, in effect of other solute on salt solubility. What is indifferent ion effect? When NaCl, like there are two different salt. One is NaCl and other is CaCO3. So here no ions are common, right? Okay. So it is completely like indifferent. They are not at all related to each other. So what will happen when NaCl is added to a system of calcium carbonate and water? So like we have a water with calcium carbonate, okay, and here NaCl is added. So we have assumed ideal condition, right? Ideal condition means, okay, that's why we were taking concentration. It is um, this kind of solution is very dilute. Okay, but if we start adding NaCl in CaCO3 solution, what will happen? The ideal condition will change to non-ideal. In different ion factors, it will change the ideal condition to non-ideal. and ionic strength will change. Okay, so instead of active concentration, we have to take activity. Okay, so here what will happen? We cannot, when there is an indifferent ion effect, concentration term cannot be used. We have to use activity. So that is important in case of indifferent ion effect. Okay, coming to common ion effect. Second is common ion effect, CIF, common ion effect. So for example, we have CaCO3. So in this whole chapter, we will take example of CaCO3 only because that is sparingly soluble salt. It cannot be completely dissolved. Okay, we have this salt. So if we add acid, okay, this kind of salt is there. What will happen if we add some acid? Let's say we are adding some HCl, any acid, it will give H plus, right? So what are the different products that will be formed? It will be Ca plus CO3 because CaCO3 is there, so obviously this will be formed. And one other thing will be formed that will be HCO3 negative. Okay, these are the products will be formed. Now, what we can see, this H plus is going to combine with CO3 2 negative, right? Then only this will be formed, right? So if we see this original equation, what is happening? We because of addition of H plus, CO3 2 negative is reducing, right? Okay. When CO3 2 negative is reducing, so to maintain the equilibrium will shift in forward direction. So more CO3 solid will be broken down to CO2 plus and CO3 negative. So what is going to happen? The solubility of CaCO3 will increase to maintain the KSP. So when acid is added, the solubility increases not because of pH change. pH change is not important, but because of the shift in the equation as per Le-Chatelet's principle. So I'll explain again what is happening here. Carbonate is being consumed by H plus. So that is why the concentration of carbonate is decreasing. So to maintain the Le-Chatelet's principle, the equilibrium is moving in the forward direction and more CaCO3 is being dissolved. So this process is called, okay, common ion effect. Because here what is happening? Because of the formation of HCO3, this equation is moving in the forward direction. And one more thing can happen, a common ion effect, if I add Na2CO3. CaCO3 is there, Na2CO3. So if I add this, this will increase carbonate. If in this equation I add Na2CO3 plus 2CO3 2 negative. So if I add Na2CO3, the concentration of this will overall increase, right? Therefore, the equilibrium will shift in backward direction for both the cases. So we will see more precipitate of Na2CO3 and CaCO3 both. So this process is called common ion effect. So we have studied indifferent ion effect. What it will do? It will change the concentration from ideal to non-ideal. And if we, what is common ion effect? It will follow the Le-Chatelet's principle and it will change the equation. Okay. there will be either increase and decrease in the product of formation of product. So next is effect of other solute on salt solubilities. So okay, so now we will see effect of other solute on salt solubilities. So competing acid base equilibria. Okay, I think we should solve one question, then we will see this. Or this is quite difficult to understand. Okay, we will see first complex ion formation. So it will be better. So a chemical species in which a cation is covalently bonded to one or more coordinating group is referred to as complex ion. So we have one, just for example, one cation, let's say Zn. It is forming bond with different compounds like OH, covalently bond with different compounds like, so such kind of compounds are called complex ions. Okay, so what happens? Uh, for example, some kind of metal is there. Okay, if we want to we want to precipitate out the metal. But in some cases, what happens? This metal is being bonded by other like OH group or ammonia group or anything. We call them ligand. These things are called ligand. Okay, they are in bond with that. So what happens? It reduces it increases the solubility of the substance. So that is called complex. So in hardness titration also, calcium ion and EBT complexes are formed, which is in wine red color. So all these compounds, no, these complex compounds will have very bright color. They are called coordinate compounds also, and they will have very bright color. So that is why in hardness test, due to the reaction of calcium 2 plus and chrome black tea, we will see wine red color. But when we add EDTA, so in burette, in hardness reaction, this is burette, right? And we have this thing. So here solution is there, and plus we will have EBT. So the color will be wine red. And here it contains EDTA. So EDTA is better complexing agent. Okay, it is stronger complexing agent. So what will happen? The color of this EDTA. So this was forming complex with Ca. Now when EDTA comes, Ca starts formation with EDTA. So the color will change. Okay, so strong complexing agent can always remove weak complexing agent. Okay, we'll see. Okay, we'll see next question. So this is the explanation of the question number one. Okay, so this is question number two. Use visual Mintek to determine the dominant species of cadmium in seawater. Assume that total cadmium is 4 microgram per liter and the ionic strength is 0.7 molar. Consider OH negative, Cl negative, HCO3. These are the possible complexing agent. So we need to use all the concentration in the given pitch table and find out the dominant species of CD2 plus. Okay, try to find out the answer of this question. We'll see the solution in a while. We'll see the solution. So CdCl2, please match this with your solution. We'll see how we are getting it. Okay. So input as visual Mintek is cadmium, ionic strength we are also putting. We have the pH, everything we have, like Cl, everything. We'll just put this thing in the visual Mintek and we will run visual Mintek and click on the button view species distribution. So this is very simple, very direct. Just getting, and what we are seeing here is this CdCl2. We're getting that maximum, right? 49.448. So here 49.45%. So among all these things, we have to ignore this HCO3 because it is coming from the atmosphere. So we will not consider that. We'll consider cadmium and chloride and sulfate also we will have to ignore. The main species, we are talking about cadmium species. So here we can see it is the maximum. So that is what we will note it down. Okay, moving forward to next question. Question number 3. The owner of the industry that generate wastewater containing both Ag plus and Hg2 plus is considering two options for discharging of water after treatment. One option is to discharge the water through an ocean outfall, in which the case the initial dilution is predicted to yield concentration of 0.04 milligram per liter Hg and 2.5 milligram per liter Ag. So this is the total concentration. The second alternative he is thinking is to discharge it in a large river for more dilution and faster. So the outfall is lower by the factor of 10. So both Ag plus and Hg2 plus are more toxic as free ions than complex. If they are free, they will be more toxic. So the major complexing ligands are chloride and sulfate. So okay, here we are talking about receiving water and river and ocean both. So both the solution are at pH 8. So the suitable disposal option would you recommend to maximize? So what we need to find in which it is forming more the time the consequence where it is forming more of complexes. That is what we need to find. You can use visual Mintek to solve this question. Try to solve this. So the answer is ocean outfall. So for ocean outfall, Ag plus we have been given as 2.5 milligram per liter, Hg2 plus is 0.04 milligram per liter, sulfate is what we have, chloride, pH, and we know the ionic strength of solution. Okay, so this is considered a non-ideal solution, so that's why we have been given ideal ionic strength. Now we'll just put everything in visual minting, and we can see the concentration of three ions. So we can see when we are putting for ocean outfall, what was the condition? That it should form complex, because that is better than the free ions. It should not be free ions. So if we look into it, we can see that the free ions is lesser for ocean outfall. See, the concentration is in the range of 10 raised to power minus 10. Okay. Similarly, we can do for river. Species distribution. Similarly, we can do for it for river, and we will get the concentration of Hg2 plus is negligible, but Ag we can see 10 raised to power minus 7, which is equivalent to other solution. So we know that since the complexes are more in ocean, so that is better. We can simply check the species distribution also while doing all these things. So the percentage of total concentration of free ions is very less compared to complexes. So mostly complexes predominate. So hence ocean outfall is suitable option. We are checking for river. After looking into species distribution, Ag plus is 36%, which is very high. Okay. So it will be highly toxic in terms of silver, not in terms of mercury, but in terms of silver, it will be high. So even the large river is not suitable for option for this. Coming to next question. Okay, so aluminum, we are adding aluminum fluoride in distilled water at the concentration of 0.1 molar. If H plus fluoride, AlOH3 are selected as components, then which is the adequate equation which will give where there is no precipitate formation? Okay, so please solve this. This is from the previous one. Okay. So the correct equation is A and C for hydrogen and aluminum. Please note this down. Okay. So we have formation equations. These are the formation equations. Please note them down. We have different components and different species. These are the formation equations. Note them down. So now next work is formation table, and we get simple equation for H plus and aluminum. The next question is, a solution is prepared by adding aluminum fluoride in distilled water. Predominant aluminum species at pH 3, 7 and 10 and equilibrium respectively are. So we need to consider that there is no precipitation. What will be the predominant species at pH 3, 7 and 10? So option A is correct one. We'll put this in visual Mintek and then we'll fix the pH and we'll see the solution. So adding zero point 0.1 molar and zero point 0.3 molar of fluoride, then fixing the pH at 3, then we can get the predominant species, the species with the highest percentage. Okay. Similarly, for pH 7 and pH 10. Very simple. Otherwise, we would have to plot everything and check in Excel. This is visual Mintek is easier solution. Coming to next question. A solution is prepared by adding AlCl3 0.01 molar in distilled water. pH can be adjusted by adding NaOH HCl into the solution. The pH at which aluminum hydroxide starts to precipitate is, here we need to see the precipitation. Earlier, whatever we were checking is based on no precipitation. Here we need to see the precipitate. Answer is 4.8. How? We'll put everything in visual Mintek. Okay. Click on solid phase and excluded species menu and then specify possible solid phases. Then simple, click on multi-sweep problem and we'll get the result. pH is 4.8. Coming to next question. A solution is prepared by adding AlCl3 into distilled water. Then out of these given species, the dominant H 3, 5 and 11. So we have checked similar question earlier. So this is few species are given. We have to check among them. The correct solution is option number D. How? Simple. All these questions we have to put in Excel, then we can prepare log C versus pH, and it can be easily seen. So that is all for today. You can leave the session now. Okay, thank you very much. We'll see solubility in detail in the next class, but I will have writing device as well.